Our subject tonight is about how fast the universe is expanding, about dark energy, dark matter, how it all comes together to form our universe today. Please give a warm welcome to tonight's speaker, Dr.
Let me grab water. Okay. Thank you guys so much for showing up to listen to me talk. I really appreciate you being here. We're going to look at how we measure the expansion rate of the universe. You've probably heard of this thing that the universe is expanding. It's expanding because of dark energy. There's a whole lot that we don't fully understand about that, and I'm going to try and unpack as much of that as I can today. Okay, so this is a general picture I like to show of how we think the universe has expanded, and I'll talk about a lot of different sections of this. But over here, this is the baby picture of the universe, the cosmic microwave background that we like to refer to a whole lot. That is the oldest light in the universe. Once that was emitted, for a long time there was no new light, and that's the dark section you see here. Eventually stars turned on, and that's this brightness, and galaxies formed, with smaller structure forming first and then eventually bigger structures forming, and we live all the way down here. That's a satellite experiment called WMAP, which I'll mention in a little bit. That's an experiment that looks at this oldest light in the universe, the cosmic microwave background. So David introduced me as a theoretical cosmologist. As a cosmologist, I like to think about everything larger than a galaxy. I don't really spend any time at all thinking about stars or planets. If you ask me questions about those, I will do my best. I will probably give you wrong answers. So keep that in mind.
So I think ask you about cake.
You can. I have so many opinions about cake. Yeah. All right. I also think about a lot of things smaller than the nucleus of an atom, because the universe was not always as big as it is today. Right now, the physics that governs the universe is the physics at scales larger than a galaxy. But when the universe was really young, it was hot and dense and compact at this end. And at that point, the physics that governed the universe was the physics smaller than a nucleus, physics at the scales of smaller than a nucleus. So as a cosmologist, I like to think about both. And as David said, I'm also a theorist, which means specifically for me that I like to think about what is the true underlying physics of the universe, what is the true cosmological model, and how do we test it? Okay, so in terms of the cosmological model, there's a whole lot that we do know about the universe. We know that it contains light or photons. Like there's light in this room, that's how you can see me and how I can see you. There's light from distant stars, that's how we know that there's a huge universe out there. We also know that the universe contains normal matter, like the stuff that makes up this table, chairs you're sitting on, us, planets, stars. All of that is normal matter. But we also know that the universe contains dark matter. This is the stuff that's holding galaxies together. No galaxy could exist unless this dark matter was kind of like giving it a little cloud to exist in. It's also giving multiple galaxies it's keeping multiple galaxies connected in a dark matter cloud. We call them galaxy clusters. Finally, the universe also has dark energy. And this is some substance we really don't understand. We don't know where it is, we don't know what it is, and it's making the expansion of the universe go faster and faster. This is sort of what a breakdown of all of those elements looks like. There's very little normal matter that's actually compactified into planets and stars. Most normal matter is something we call dust. It's just diffuse, it's gas. It hasn't coalesced into something dense. A much larger chunk of matter is in dark matter. There's essentially no energy in light. Even though there's so much light in the universe, everything else has a ton more energy that it contributes to the universe. And then finally, the largest chunk is taken up by dark energy. So you might look at this and say, okay, so we don't know anything. We don't know where 95% of the universe is. Cosmologists, you have misplaced 95% of the universe. And to that I say, you don't know where it is either. And two, we also don't know what's like under 70% of our planet. 70% of this planet is underwater. We don't know anything that lies under the crust of the Earth. We still don't actually know what's going on with whether there's an iron core, what else is going on under the Earth's crust. We don't even know 80% of the animal species that are on land. So there's a lot of unknowns in science. But one thing that we do know is that the universe is expanding. We're very confident about that. And it's expanding in a very specific way. It's expanding isotropically, which means the same in all directions. Pick any one of these satellites. One of these galaxies. All the other galaxies are moving away from that one. So it's the same in all directions. It's also the same in all locations. If you switch from the galaxy you're concentrating on, instead of the red one, look at the green one, the expansion looks the same. Everything seems to be flying away from the green one too. This expansion we can then measure as how fast are things moving away from us based on how far away they are from us. Objects that are further away need to move away from us faster so that these two conditions are met, which we're pretty confident about that these are correct. With that, we can measure the expansion rate of the universe. It'll look something like speed of recession of an object versus divided by the distance of that object from us. Okay, so how do we really do this? We measure the expansion of the universe by using something called the Friedmann equations. These connect how fast the universe is expanding with how much energy content there is in the universe and how fast this expansion is accelerating. Because the universe doesn't only have this isotropic and homogeneous behavior, we also have galaxies that are dense, but there's nothing between them, so there's a void. We also have to think about all the perturbations in the universe. I'm not going to talk about any of that right now. This is the only equation I'm going to show you today. And specifically for this equation, I want to concentrate on the denominator. Turns out measuring distances in cosmology is really hard. Like if I wanted to measure the size of this room or the distance from here to my car, I could literally count my steps. I could use a massive measuring tape, but we can't go to the next galaxy. For light to go to the next galaxy is going to take 1 million years. For light to go to the next galaxy cluster, it's going to take 100 million years. So we really can't go there and measure the distance between us and that. We have to come up with other ways of measuring distances. Two of the ways we do that are standard candles and standard rulers. And I'll talk about these two ways specifically because these are both how we measure the denominator of that equation and therefore measure the expansion rate of the universe today. Okay, so we have a few different ways of measuring the expansion rate of the universe. We can use stellar distances, or we can use the oldest light in the universe. We really don't use radar guns. Can't do that. Okay, does everyone have their phones? I know you silenced them, but let's pull them out for a second. And I'm actually going to steal my phone back from you. Thank you. Okay. Turn on the torches in your phone, the flashlights. And I'll do the same. All right, and now point them at yourselves. Okay, now look at that flashlight and then look at this flashlight. One of them is dimmer. Which one is dimmer?
Yours.
Yes, mine is dimmer just because it's further away from you. I'll wait for everyone to forget to turn off their flashlights now. Okay. Also, we look pretty silly doing that. Anyway, one of them is dimmer. And just based on that, we try to figure out how far the object is. For an object of known brightness, its apparent brightness, its observed brightness, can tell us how far away it is from us. And that's what a standard candle is. It's any object whose brightness we can calibrate, we can know, without actually thinking about how bright it appears to be to us. For standard candles, we can use a lot of different kinds of objects. The one that winds up working really well are supernovae. These are incredibly, incredibly bright stellar explosions. More specifically, we want to use type 1a supernovae. What's happening in this specific scenario is you have a white dwarf and a red giant that are in a binary, they're orbiting each other, and the white dwarf is eating away at the red giant. So it's gathering more and more mass from the red giant. At some point, it gathers just enough mass, and it reaches something we call the Chandrasekhar limit. At the Chandrasekhar limit, the white dwarf is no longer stable. It's the gravity of its mass and the pressure that it can generate to keep its size no longer balance. So it essentially implodes, collapses, and then it explodes. And it explodes at a very specific mass and therefore a very specific brightness. So it becomes a standard candle, an object of known brightness. Then, knowing how bright it should be and knowing how bright we see it to be, we can figure out how far away it is from us. All right. Specifically, these types of supernovae are incredibly, incredibly bright. This is a really fantastic visualization of supernovae essentially going off in a galaxy. I really like this because sometimes I don't even notice that this galaxy is there until a supernova goes off in it. And then I'm like, oh, there's also a galaxy over there. There's also a galaxy over there. So these go till really, really far out, which means we can measure the expansion of the universe up to that distance using these sorts of objects. Here's another image. This is actual data. The previous one was just an artist rendition. This is a supernova going off in M82. And you can see this little bright spot appear here. That bright spot outshines an entire galaxy of stars. These things are incredibly bright. So we can figure out how far the supernova is from us. So we have that denominator for the equation. We can figure out the numerator, or its speed of recession, by looking at spectra from the galaxy and looking at how those spectral lines have shifted. Because you're all astronomy enthusiasts, I'm going to assume you've heard of redshift and Doppler shifts. So this is just that. It's just a shifting of the spectrum because the object is moving away from us. So we get an expansion rate by equating the two, and we find that the universe should be expanding at about 73 kilometers per second per megaparsec. I will not convert that to miles. So a megaparsec is about 3 million light years. So if you had a galaxy that was sitting 3 million light years away from us, just because of the expansion of the universe, it would be moving away from us at about 73 kilometers per second. So we figured out the first part of this. We figured out how we can measure the expansion rate using stellar distances. Let's talk about the second part, the oldest light in the universe. This is what I do for a living. This is like my favorite thing in cosmology. This is the other half of the two distance measures that I was talking about. We've talked about standard candles so far. We're going to talk about standard rulers now. It's very similar. It's essentially, if you have an object of known size, based on how large you observe it to be, you can figure out how far away it is from you. And here's an example. The elephant on the extreme right versus the elephant on the extreme left. If you were to look at this image, you would just assume, yeah, those elephants are probably the same height. And you're doing that because you're intuitively recognizing that there is a standard elephant-sized ruler. And you're using that to recognize that this elephant is much further away from you. We're essentially trying to apply the same principle, but now with cosmological observations. So for this, we specifically use a baby picture of the universe. It's a baby picture because the universe was only like 400,000 years old. It's so young. To be fair, the universe is now about 14 billion years old, which is much, much larger than that number. We've been looking at this baby picture of the universe for a really long time, literally longer than I have been alive. I don't know about you guys. So this is what it looked like when we first observed it in the 1990s. This was using COBE, which is the Cosmic Background Explorer. We then saw it with the WMAP satellite, which is also in your newsletter. It was fantastic. There's a whole portion about this satellite in the newsletter. WMAP is the Wilkinson Microwave Anisotropy Probe. And then most recently, we've made a full sky map of the cosmic microwave background, or the baby picture, with the Planck satellite. OK, so what is that map actually telling us? So that baby picture of the universe is coming out from a time when the universe was really young. It was hot and dense, so hot and dense that matter was essentially a plasma. It was in the fourth state of matter. Everything was a plasma. So protons and electrons in this plasma were attracted to each other just because they're oppositely charged. And then anytime you have a charged particle, light likes to interact with it. Light kind of bounces off of it, and light was essentially trapped inside this plasma. Also, this light was really energetic. Anytime you had a proton and an electron trying to combine into neutral hydrogen, a photon, a light particle, would just come and break it apart immediately. So you didn't have a universe that could become neutral. It stayed a plasma. And like I said, photons were trapped in this plasma. They couldn't travel very far. In this plasma, there were a bunch of oscillations. You could have one portion of the plasma be slightly more dense. Let's say one portion of the plasma has slightly more dark matter, right around here. That dark matter, because of its gravity, is going to attract more plasma towards it. That plasma will get heated up because there's now a huge density of plasma there. And so plasma pressure will then push it back out. So we had essentially waves in this plasma. There were regions of like more density, there were regions of less density, and these were essentially just oscillating between them. Eventually, though, the universe continues to expand, and as it expands, it cools. The light particles cool, and the matter cools. At some point, the light particles cool and lose enough energy that they can no longer break up atoms, which means that the universe suddenly becomes neutral. A neutral universe does not trap light anymore. So these photons travel away, and with them, they carry essentially an imprint of what was going on with these oscillations. That's what the cosmic microwave background is. It's an imprint of what the universe looked like at the time, and these regions correspond to regions of more density and less density. Specifically on this map, the blue are more dense regions, and the red are less dense regions. Okay, going from this baby picture all the way to today is really, really complicated. It's not easy to figure out how we evolved from here, and in those regions of more density, galaxies formed, stars formed. In the regions of less density, there was nothing, maybe just some diffuse gas. So we're going to play another game. Okay. This is not even a fair game because I'm making it really easy for you guys. Instead of a baby picture of the universe, we now have a baby picture. One of these is me. The others are my sisters. For a fair comparison, you would be trying to relate the baby picture to the adult if the babies were a few hours old. That's how early we have that snapshot of the baby picture. Okay. All right. So who thinks the correct baby is A? Okay. Who thinks the correct baby is B? Cool. Who thinks it's C? Okay. Not bad, guys. I'm glad you're at least participating. The A's have it. This one is me. So the A's, you would make great cosmologists. Okay. But going back to this baby picture and trying to understand how we go from here all the way to here, we're going to also think about how the universe has evolved from here to here. which means we need to think about the stuff that's in the universe. We need to think about what was going on with dark matter, what has been going on with dark energy more recently, how has everything else evolved, how did the galaxies form, how did stars turn on. All of that goes into going from here to here. So it's a really complicated process, but we can use that fact to actually learn more from it. Specifically, I said that the baby picture evolved into the universe today, and it turns out that the regions of overdensities in the baby picture, the regions of more densities, which eventually evolved into galaxies, those have a preferred separation between them. They have a preferred separation between them here, and we also see a preferred separation between galaxies now. And we can relate these two. That is what becomes our standard ruler, the preferred separation between patches on the cosmic microwave background and sets of galaxies, clusters of galaxies. This is an artist's rendition, but it's kind of what is going on. We see a cluster of galaxy here, and then the next cluster of galaxy has a preferred separation that is roughly the radius of this circle. This is, of course, an artist's rendition, but we now have phenomenal data from the dark energy spectroscopic instrument. It's been coming out super recently. If you're seeing articles in like the New York Times about how dark energy is broken or cosmology is broken, it's because of this experiment. This is really, really exciting data. Like the last release was like a week ago, 2 weeks ago. Like it's super fresh. We're very excited about this. This is what it actually looks like, the separation between galaxy clusters. Every dot you see in this image is a galaxy. It's another whole Milky Way. And if anyone's interested, that QR code will lead you to something like a video game map where you can essentially fly through this actual data set, and every dot is going to be a galaxy, so you can kind of move your screen around and you'll literally be like flying through the actual map of our universe. So it's really cool. I can also send this out through David later.
Yeah, okay.
Yeah. Okay. So how are we going to use the standard ruler that we finally come up with to measure how fast the universe is expanding? I told you that there's a preferred patch size here, which winds up being the preferred separation between galaxies currently. When we looked at the image of the elephants, you had a small elephant that was far away from you, and then you had a much larger looking elephant that was closer to you. That difference in size, perceived size, was only because of distance. But in cosmology, we don't only have distance, we also have expansion with distance, because the universe has been expanding the entire time. So if you see this red line here, the dotted red lines, that roughly corresponds to what the size of the separation between galaxies should have been if we were only looking at distance. But there's more. The actual separation winds up being closer to the blue curve, and that is the one that's accounting for the expansion of space. So space expanding magnifies, essentially, the separation between galaxies, and that's how we get a number out of this for the expansion rate of the universe, which is this number here. And that is a very different number, in case you have been paying attention. And this number, I should put a massive asterisk on it, because it absolutely depends on all of the assumptions we made in this red arrow. To go from here to our current times, we assumed that we know a lot of things, like how does dark matter behave? How does dark energy behave? That dark matter doesn't interact with normal matter or normal light. Dark energy doesn't interact with normal matter or normal light. Dark energy is diffuse. It's everywhere in a low density. It's not clumping anywhere. Dark matter is clumping. We've made a lot of assumptions about these things. So that's a huge caveat for this number. All right. I said we were going to measure the expansion of the universe in two ways. We have now done that. We've used stellar distances. We've used the oldest light in the universe with that big asterisk. And we have two very different numbers. The thing is, these numbers are, at this point, 5 sigma discrepant. 5 sigma is a number that we really love in physics. It's an important number, and it essentially means that there is less than 1 chance in 3.5 million that this is just a fluke. That's a very, very tiny chance. At that point, we're pretty sure this is real. So we like to use this 5 sigma level to test whether physics is real, any results are real, or they're just going to go away from statistics. Okay, so why is this disagreement even exciting at all? It could just be that we were wrong about the supernovae, about the exploding stars. We've done something wrong on that end. It could also just be we somehow measured this image wrong, the baby picture of the universe. But the most exciting part for me is maybe there's something interesting going on with all of this dark 95% of the universe. And this is what I spend most of my time thinking about. With that, I will stop here and I'll take any questions that you have. And yeah.
It's the same order of magnitude. It doesn't seem that, given all of these unknowns, it seems like they really are about the same. How do you get that it's 5 sigma different?
Oh yeah, that's a good question.
There's so much that's not really known.
Yeah, for sure. It's because of these numbers here. That's how sure we are in these measurements. We think that this measurement is correct to within 0.5. We think this measurement is correct to within 0.9. Those are too different to be covered by just that much uncertainty. If we were a lot more uncertain in these measurements, I completely agree with you. It would not be a problem.
Measured in such different ways, and there are lots of assumptions going into each of them. So, and they're the same order of magnitude, so you really are measuring.
Yeah. So this is not the first Hubble tension that's been in cosmology. The first Hubble tension was a difference between 50 and 500. That was before the 90s. I'm sorry?
At least that's an order of magnitude.
Yes, but since then, like if you look at, for example, wrong direction. If we look at this sort of thing, we have become incredibly good at measuring the universe. So these little differences, which are far smaller than an order of magnitude, are really beginning to matter.
Because we're so much better at it.
Because we're so much better. All of our measurements are really precise. Yeah.
So all over my Facebook feed is which of course means this is correct, is that the possible solution to this issue could be the rate of change of the expansion is not stable. It could change over time. And so we don't have a standard rule because physics is not unknown.
That's a good question. Let me see if I have. No, I don't know if I have a good image for that. I think this is the image I'm going to wind up using. The rate of expansion of the universe, 100% is changing the entire time. It has always been changing, but we account for that. So the way that this curve looks, the way that it's bending, that is accounting for how the universe's expansion has evolved over time. So just the rate of expansion being different is not going to account for that. It has to be a very specific difference from what we think. It has to be a very specific departure from the standard model of.
What I was reading it is that it's not stable. It's changing in ways we don't understand. I think that's what came out of that recent data or something.
Yeah. So that part is yet another different thing. So one of the really cool things that came out of this data is that dark energy is not stable.
Yes. Yeah.
So largely, when we have been trying to build a standard model, so to say, of cosmology, we have been assuming that dark energy is this super stable energy density that permeates the universe. We think that even though the universe is expanding, an energy density should be energy over volume. Even if there's more volume of the universe, the energy over volume stays the same. So as there's more volume of the universe, there's also just more dark energy to compensate for it. That's what we have been always thinking about how dark energy behaves. This new dataset is telling us maybe that's not the case, and dark energy's density is evolving over time. However, that worsens this tension. So if we take the standard rulers and we use that to correlate the baby picture and these galaxy clusters, with the evolution added for dark energy, it's going to reduce this number even more. It becomes like 66, 65.
Oh no, that's more different than the 73.
Yeah. yeah.
How do you calculate the error bars on that measurement, the 0.5? How do you know it's not 0.49 or something like that?
Yeah. That's a really good question. It's completely dependent on, do I have that still? It's completely dependent on this stuff. So if you had a slightly different model, and this is the part where, this is the actual research that I do, I try to come up with different models. I try and change up some of this stuff to change that number. So I come up with a different model for how the universe has evolved. And if you have a model with more parameters, usually that means your error bars will blow up. You have more uncertainty because you have the same, say you have the same number of data points, but now you have more parameters that are all trying to fit those same data points. Your uncertainty in those parameters then goes up. And that is going to change this error bar. So specifically in the model that I work on, the error bar is essentially doubled. I can come back to this question if you want to chat more, but I'll take another one.
So which number do you like better?
I just like that they're different because that's why I have a job. Yeah, sorry.
I was going to ask about this new finding.
Yeah.
Decreasing energy.
Yeah.
Well, two questions. One, energy can't just disappear. Where is this decrease in energy? Where is this energy going? Is it some other kind of energy, or is it dissipating as heat? Or
Yeah.
The second question is it possible that there's like a, I don't know, third derivative or something where it was expanding at one rate at one time, then it went faster, then it went slow?
These are very good questions. Okay, so the first one, where is the energy going? You're absolutely right. Energy is not being created or destroyed, but usually we think about energy conservation in this sort of space where we're not traveling at speeds close to the speed of light, and we're not thinking about, we're essentially, if Euclidean space means anything to you, we're essentially thinking about only x, y, and z directions in space and time. X, y, and z directions are not changing with time. But if you think about the universe is expanding, which means the x, y, and z directions now become functions of time. So energy is no longer conserved. It's an energy momentum. You know what? I am going to go back to my April Fool's slide. We'll get there eventually. The point is that the energy momentum tensor, which is a more complicated thing, that is the thing that's conserved. And in a sense, it's really this stuff. It's energy densities that are conserved. Or really energy densities are driving the expansion. So what winds up happening, for example, let's start by thinking about just normal matter and what's happening to normal matter. So we have, for example, literally galaxies, which are clumps of normal matter. If my space expands, the number of galaxies has gone down in this volume. So because volume is increasing as length cubed, the amount of energy density in my normal matter is going down as length cubed. The energy density in light is going away faster because as space expands, it's also stretching out the wavelength of light. So we're going from like, say, X-rays to IR waves, infrared. So X-rays are substantially more energetic than infrared. If we stretch out the wavelength, then we're losing energy. And we're losing the number of photons in the universe because, again, they're also subject to something like length cubed. So then for photons, it becomes length to the fourth. So this energy is still there in the universe. The energy density is, essentially like energy is going down just because space is expanding. And then the second question was about the new stuff.
Weird third
Yeah,
derivative.
there is actually a really fun thing going on, which is that in terms of what's going on with dark energy, what this specific experiment found, there we go, is that, so if dark energy is evolving with time, if you think about the first thing that is not constant, you might think about a line which is tilted. It's not constant. Different parts of the line are at different values. But you can think about more complicated things. Instead of just a line, it can be a parabola, it can be a sinusoidal function, it can be something substantially more complicated. So the first thing we tested with this new data was whether it's just a line with a different slope. That didn't seem to fit quite as well. And it turned out that there is an appreciable second derivative to however dark energy is evolving. It's doing this really funny thing where the energy density in dark energy was actually growing at early times, and now it reached a peak at a few billion years ago, and now it's going down again. So there is something interesting going on. We don't fully understand what it is. Yeah. This is fresh off the press.
Yeah.
Yeah. Let me go there, and then there. Okay.
So DESI is the new kid on the block. What's the next tool to observe?
Ooh, it's a really good question. It's almost a political question, because I would want to say the experiments that I'm closer to and I'm more involved with. DESI is going to have another data release itself. So this is not the final DESI boss. There's going to be more. Then there are a bunch of other really incredible experiments coming up. Euclid is already up and out there. Euclid is a satellite experiment. It's at the Lagrange point 2. It's not on Earth. And it is going to scan the sky, and it's also going to give us a whole bunch of supernovae measurements. It's going to do some of this stuff, do some baryon acoustic oscillation. It's going to do a whole bunch of really incredible stuff. Because it's a space-based experiment, it has a lot more. It's just going to have much cleaner data, a lot more data. It can observe substantially higher fractions of the sky. So that's going to be a really cool experiment. Roman is fantastic, but Roman is really far future. Forget Roman. Forget Roman for now. Okay, Rubin is going to be incredibly cool. Rubin is a ground-based experiment, but it's going to scan the entire sky multiple times a day, which means any time a transient goes off. A transient is anything that's blip and you've missed it. Supernovae are transients. The explosions. They don't stick around all the time. So Rubin is going to increase the number of supernovae we have observed by multiple orders of magnitude. There's going to be so much data that one of the genuine things we need to figure out in science right now is how to build pipelines to take in that data and actually look at it, because there's just going to be so much of it that in a million years we're not going to get through it. So we have to start adding in AI and automating a lot of these things, because we genuinely cannot look at so much data. Forget about storing it, because it's multiple terabytes of data an hour. It's insane. So those experiments are going to be really, really exciting, super next level. I'm slightly more partial to Rubin because I'm more involved with the people who are working on Rubin, but they're all really, really exciting experiments.
Who's running Rubin?
It's again multiple collaborations across several universities. There's a lot of people who are working on Rubin at U Chicago, and those are the people that I work with. So yeah.
How do
Okay.
you spell Rubin? R-U-B-I-N?
RUBIN. It's also called LSST, the Legacy Survey of Space and Time. It used to be called the Large.
Synoptic supernova telescope.
It was Large Synoptic Survey Telescope, I think. And then they changed LSST to Legacy Survey of Space and Time, and now it's just called the Vera C. Rubin Observatory. Yeah, I'm glad it's Vera C. Rubin. Yes.
Can you go on again? Dark matter was less dense, then more dense, then its density is changing around instead of expanding like you expect it to?
Dark energies, yes.
Dark energy.
Dark energies.
And how do we know that when we can't even see dark energy?
We essentially don't see dark energy, we see its impact on things that we can see. So dark energy impacts how the universe expands, and we can see how the universe has expanded over time by, for example, looking at these galaxy clusters to really far away distances. As we look into space, we're always looking in the past. As we look further away, we're always looking further in the past, which means we can essentially, if we can look really far into the past, we can draw a timeline for the universe. And based on that, we can figure out how it's been expanding. And that's kind of what this experiment is doing.
But it was expanding fast sometimes and slower at others.
No, this is about the second derivative thing that we were talking about. So it's always been expanding. It has never contracted so far. The thing that's changing is how fast it's expanding.
The rate of expansion. So the rate
Yes.
of expansion sometimes changes.
Yes.
And that is
Yes. It's something unexpected, I guess. Yeah. Let me go to the question back there. Yeah.
Something I've always had a hard time understanding with the BAO stuff is going from the 2D map of the
Yeah.
CMB to what's obviously measuring it, 3D structures.
Yeah.
How much of the Hubble constant calculation is based on that transform, and how much is just based on just the raw measurements of the galaxy structures that you're measuring with
Yeah.
instrument like DESI?
Yeah.
And then also DESI's, kind of an unusual telescope. I don't know if people might be interested in hearing about the way it operates, if you were able to share that.
The second question is a fantastic question. I am a theorist. I do not think about that.
I work on the experiment, so I can.
You should do that. Yeah, please. I was wondering why you're just talking about like BAO and throwing that around.
So the DESI instrument was built on a telescope that was outside of Tucson. It was originally built in the late 60s, early 70s. We put a new instrument on it, I forget, 7 or 8 years ago. It's not a regular camera. It actually has, where the focal plane is, small robotic manipulators, each with a fiber optic on it. So you get the light. Knowing where you're going to point the image or point the telescope, you have a map. You position all the fibers to where you want. So the light from one galaxy falls on one fiber. It's I think it's about 5,000 fibers. The fibers run down the physical structure of the telescope down into the basement, where it's light sent through prisms and shines onto CCDs. We built the CCDs here at Fermilab. And then you get the spectrum in lines on the CCDs, so it's doing the spectral analysis of each galaxy. So it's a strange. It's strange as a camera, but it's fascinating to see the picture here representation.
Yeah. It's an incredibly cool, incredibly powerful instrument. Thank you so much for that explanation. It was delightful to hear it. So the fact that it is able to get all of these spectra for so many galaxies so fast is completely unprecedented. DESI's predecessor was the Sloan Digital Sky Survey. In the first data release of DESI, which happened last year, they had, correct me if I'm wrong. If anyone in the room knows, correct me if I'm wrong. I think they had roughly the same number of galaxies as SDSS, which was the predecessor, just in their first data release, because they're able to get these spectra so fast. And the spectra are really important because they tell us how far away any given galaxy is. We couldn't build a map like this without knowing the precise locations of these galaxies. Now, in DESI's second data release, which is 3 years of data, the first data release was 1 year of data. In 1 year, they outdid 12 years of Sloan Digital Sky Survey. In their 3-year data release, which was this year, they have more than doubled that sample. It's several million galaxies, if not like billions of galaxies and their locations. And that is why we're able to get such very fine information on how the universe is evolving and what dark energy is doing. So it's really cool. And then for your first question about going from 2D CMB to 3D BAO, the thing is that we can actually, let me see, where was I? We can get this measurement, roughly this measurement, from just the baby picture without any information on baryon acoustic oscillations, which is the standard ruler that I've been talking about, the galaxy cluster separation. We can do that because this is so much information. Like, I know you see this like colorful map that looks a little bit like vomit, but it's not. It's really, really cool. What we like to do in cosmology is think about, actually I'm not going to go down that because that's a rabbit hole. But let me go back a few steps to this image. Okay, so you can see that there's a lot more detail here. There's less detail here, there's even less detail here. At certain scales though, at one specific scale, if we had resolution at exactly that scale for this map, you would see the most variation. If we go to a scale smaller, you would see less variation. If we go to a scale larger, you would see less variation. I'm going to go use the whiteboard actually. So it's essentially something like scale, and variation. And the cosmic microwave background looks, whoops, that's terrible. I'm going to draw that again. It looks kind of like this in terms of scale and variation. So that's a very complicated looking function. You can't just fit it with a polynomial. You can't fit it with any kind of line. It's a very specific looking function. That specificity, weird word, specificity gives us a lot of information about everything that's going on with the universe, about dark energy, dark matter, whether these are interacting with normal matter, how much light there is, all of it. And just that can tell us how fast the universe is expanding. We try to include the galaxy clusters though, because it's following the same physics. The physics of this stuff is the physics of where was more matter, where was less matter at the baby picture of the universe. Galaxy clusters are where is there more matter and less matter now. It's the same physics, the same standard ruler. So we do like to combine these to confirm that nothing funky is going on between them, that everything we have thought about for dark energy, dark matter is correct, and extract an expansion rate from both of them together. That extraction also helps us break important degeneracies in parameters. That just means that if I increase this parameter and simultaneously decrease this other parameter, I can fit my data as well. That's called a degeneracy. So I can change both these parameters at the same time and everything will still be fine, which means I can't tell these two parameters apart. That said, the other thing we can do is the reverse. Not use this at all, but only use the galaxy clusters. Only use this information. To do that, if you were to just use exclusively this dataset, you don't get that much cosmological information out of it. You still understand that if the universe is expanding x fast now, it was expanding 0.5x fast at this point, or 1.5x fast at this point. But you don't know what the x is. To understand what the x is, you need to essentially anchor this, calibrate this, using the baby picture. So when we use them together, we get a wealth more of information than we do when we use them apart. So we like to use them together. Yeah.
Do you overlay those pictures to get that anchor?
Yeah, it's a good question. Yeah, we sort of overlay them. What we more specifically do is figure out what this size should be here, and then use that size here, and then essentially say, okay, if this is my standard ruler, then I can directly get a distance out of it. Yeah. If that makes sense. Yeah.
Talking about the baby picture that you showed about yourself and the other two sisters.
Yeah.
Remember? Okay, so I thought you were number one because in that picture you look more curious.
I think there's also a book in front of me which helps. Yeah, there's like a book in front of me.
Yeah, and more naughty.
Oh, thank you.
So what other two sisters doing? What are they doing?
This one is in film and television, but behind the scenes.
Behind you?
Sorry?
Behind the scenes. Behind the, oh, okay.
She's behind the scenes in film and television. So she's essentially deciding what kind of film and television to produce. So she decides who to give money to.
Where is she?
She's in LA.
Oh, LA is nearby. Oh,
Yeah.
right.
Yeah. And then this one is currently in Singapore. She is working for the brand that owns Tim Hortons and Burger King and all of that stuff. Yeah, but she's essentially kind of brand managing.
And you are located
I'm located here in Chicago.
in Chicago?
Yeah. Yeah.
Very nice. So how come you become so intelligent at your age? You're all very relevant. Please, enlighten.
I honestly don't think I'm very smart generally in life. I'm just good at one thing. It happens to be this thing. Yeah. Yeah.
I see in your baby picture there's a blue pen. What were you contemplating on writing down?
Okay, honestly, I think the most likely explanation, knowing all the stories I know of myself when I was a child, is that I found that pen. That is my grandfather in the background. He was a lawyer. He was like phenomenal lawyer. And I was probably using that pen to scribble on all his books, and he's trying to take it back from me. Yeah. Yeah.
I had a question. When you measure a distance from a certain galaxy, a certain amount of light years away or miles, given the fact that the universe is expanding and further away it is, as faster it's going, when you say the distance from this galaxy is this, that's only at that point in time, because it's constantly changing, correct?
Yeah, so distances in cosmology become really complicated really fast. There's several different kinds of distances. So for example, when we were talking about the standard candles, the supernovae distances, that's something we call a luminosity distance, because it's the distance from point A to point B as the intensity of light falls away. The kind of distance that we use here is a different distance. It's called an angular diameter distance. So if I go back to the elephants, what you were really doing when you were looking at the image of the elephants and figuring out these elephants are probably the same height, you were comparing their angles. One subtends a larger angle to your eye, the other subtends a smaller angle to your eye. Then there's also the distance that we usually use to answer your actual question is a co-moving distance in cosmology, which is most similar to this sort of distance. We divide out the expansion of the universe as we go back in time, and we just assume, let's set the scale to whatever it is today, and we're going to measure the distances between these galaxies by subtracting out the expansion. So if these galaxies were closer together in the past, we're just subtracting out that expansion, not subtracting out, dividing out that expansion, and it would just essentially be the same co-moving distance. Yeah. Yeah. Oh, sorry. I'm so sorry. Yes.
The type 1 supernova, type 1A supernova, did you have to calibrate that using a different method, like set the variables?
Yes. Okay, I have another slide for this, which I will need to find, but I can find it. I think this is the slide I want. Yeah, that should be. Okay. So what's actually happening, these supernovae are, they're very rare. We like to say that we have one supernova per galaxy per century. We're not going to live several centuries. We're trying to do the science now. So we need to find a way to figure out how bright the supernova should be by using other means. We've seen a lot of supernovae because we can see a lot of galaxies, But exactly how bright should the supernova be? When I said that we use the Chandrasekhar limit and we use this white dwarf eating its companion and it explodes with a very consistent luminosity, actually doing all the physics out to determine what that luminosity should be using pen and paper becomes really difficult. So what we do is an empirical calibration. We go out and measure how bright these supernovae are at a distance that we know of, and then we use that to figure out how bright the supernova should be at 0 distance. So to figure out what the distance to the supernova is, which is now the reverse problem, now we're not using the supernova to find out distance, we're trying to use distance to find out brightness of the supernova. We use essentially Cepheid variables. We also use a bunch of different anchors, but Cepheid variables are the main ones. Well, I should not say main ones. There's a bunch of different anchors. I'll just talk about Cepheid variables for now. These are really bright stars, but they're not bright enough to be able to be seen in other galaxies. So specifically for Cepheids, they have a relationship between their luminosity, their brightness, and their period. So over time, their luminosity is changing. And if we know how this luminosity is changing, let's say it cycles fully every 3 days, then we have a relationship between that period and brightness, and we can figure out exactly how bright the Cepheid should be. We also use, let me go back to this, whoops. Okay. We can also use parallax to figure out the distances to Cepheids within our own galaxy and within the Large Magellanic Cloud, which is super close to us. Okay, show of hands, who is not familiar with parallax? Okay, cool. So parallax is essentially, we can do this now. Close one of your eyes, put out your thumb, and block out my head. Okay, I'll now move. Okay, now switch eyes. Your hand is no longer blocking out my head. And that's just because there's a distance, there's a displacement between your two eyes. And so a close-by object moves against the background when you switch eyes. The same thing is happening with us going around, the Earth going around the sun. There's no sun here. What am I doing? The Earth going around the sun. When we're on one side of the sun versus the other side of the sun, nearby stars seem to move against background stars which are so far away that they don't move. Based on how they move, we can figure out how far away they are. So let's do this for Cepheids. We can use parallax because Cepheids are close enough. We can do this. So we use, for example, the Gaia satellite, which very recently got decommissioned, to figure out how far these Cepheids are. Once we know how far away they are and how bright they are, we can then use this relationship between their period and luminosity to see how bright they are in a different galaxy and figure out how far away they should be. Because now we know their brightness, we know how bright Cepheids are closer to us. So now we can use the luminosity distance to figure out how far away this galaxy is. Now that we've gotten far away enough, we have a lot of galaxies at that distance, not just us and the Large Magellanic Cloud. There's a whole lot of galaxies once we move a little bit further away in distance. Those galaxies have supernovae, which is very exciting because now we can use the same thing. We know the distance to that galaxy and we know how bright these supernovae are, which means we can use the we can use the brightness of that supernova to go even further away and figure out the distance to that galaxy, because we have now calibrated the brightness of a nearby supernova. The reason that we have to do this, we have to keep stepping away. We call this a distance ladder. It's built on standard candles. Cepheids are actually another kind of standard candle because with their period and luminosity relationship, we can figure out how bright they are. We need to go really, really far away because, for example, Andromeda is going to crash into us, into the Milky Way, in some billion years. Million years? I don't remember. Maybe you guys know better. But there's galaxies. But the thing is that galaxies are all moving. They're not just sitting there, standing still, waiting for us to measure them and measure the supernovae in them. So if I were to measure things in Andromeda, it would actually look like the universe is collapsing, like it's going to be a big crunch. But that's not true. The universe is expanding. So we need to go far away enough so that the smaller motions of these galaxies, which are called peculiar motions, don't matter. And most of the movement of the galaxy is simply because of the expansion of space. Yeah, so we build a distance ladder out, calibrate the supernovae, and that's how we actually get the Hubble.
So, are all Cepheids the same so that you really can? If you get one close, you know everything. Then are there variations?
Yeah, I'm going to go to the board again. Okay, there's a lot of debate about this. There's definitely variation. All the people who are smarter than me who actually do this completely disagree about what this variation should be. So let's just go with period luminosity relationship. And Cepheids kind of look like this. But there's a decent amount of variation. What we do is just draw a line through that and then have an error bar on that line.
Oh, okay.
And then what the error bar itself should be is still under debate.
Okay.
So when I showed you all of this and I showed you a measurement for the Hubble parameter, that error bar is under hot debate. Yeah. Yeah.
What's the universe expanding into? I know there's a saddle shape, this shape. Well, if you have a shape, you're defining an area. So I don't understand what it's going into.
It's okay, so there's a few different answers to that question. One answer is simply we're used to thinking about how the universe is expanding with the analogy with a balloon. You know, you blow up the balloon's expanding, two different dots on the balloon are moving away from each other. But that's not really what's happening. The expansion of the universe is not about the universe expanding into something. It's about space stretching between two objects. So it's not that it's expanding into something that is outside of it. It's just that there is more and more space between two things. The other answer to that question gets very comic book very fast, because then we get into multiverses, and you can talk about bubble universes and how you could have Okay. There was this image that I used at the very beginning of my talk about how the universe, the expansion of the universe, what that looks like. This one. Okay. So at the very beginning of the universe, this point was something called inflation. The universe exponentially expanded very, very fast. Huge amounts. It became essentially 10 to the 60 times its original size. So 10 with 60 zeros behind it.
Oh, Gould stuff.
Yeah, like it was in seconds. That's called inflation. There's a lot of weird theories about inflation, and a lot of theorists will argue that they all lead into multiverses. Once you have inflation, you don't necessarily have the same amount everywhere, which means different parts of the universe would have expanded differently, and that's already kind of a multiverse. So one bubble universe could be colliding with another bubble universe. But a lot of this is very difficult to find empirical evidence of, to find actual observations that will support it or refute it. So it's a cool theory to think about, but I don't know too much about it. I think more about models that I can test. Yeah.
On that, there was some discovery recently that there's a difference between the way some galaxies are rotating. They're rotating in one direction, and someone theorized that one explanation is that we're inside a black hole that's spinning. This is a recent hypothesis.
That is.
Or observation.
Okay.
And it was a study of the directions in which galaxies are turning.
Okay. I don't think I know anything about that.
That came out in the last couple of weeks.
Okay.
And,
Okay.
When was it reported? Maybe it was on Sean Carroll's podcast, or maybe it was on
Oh yeah, Sean Carroll's really cool.
Yeah, well, he has a great podcast.
Yeah.
No, it was another science podcast.
Okay. Okay. Sorry.
But it was authoritative. That is.
Yeah.
It is a
I hear
real
you.
theory,
Uh-huh.
but the explanation is.
Yeah, the we live inside a black hole has also been invoked as an explanation for dark energy,
Right.
but I haven't seen any like testable predictions of these models. So yeah.
Can you explain a little bit more just about dark energy in general? Like, is there a way to measure it? How do you compare it to normal energy?
Yeah, so this dark energy is a term that was coined, but it's not necessarily a term that you should think about intuitively. Let me say that. How we measure dark energy is, like I was saying before, we have to look at its impact on other things. So we have to, for example, in terms of this image, we have to look at its impact on galaxy clusters and how those are moving away from us at various different slices in time.
So I kind of wonder if there's magnetism to it or gravity-based or...
Yeah, so dark energy was written down by Einstein in his like very initial field equations. You know what? I am going to go back to my April Fool's slide again. Okay, this thing. Einstein called that his biggest blunder. This is dark energy, that lambda. It's something that was essentially just added to his equations because he didn't like that the universe was not static. He didn't want it to be evolving. But it turns out even with that, it is evolving. So it's not necessarily something that you should think of as energy in the same way that we have energy in like these lights here or magnetism. It is some kind of an energy density that permeates space. And it seems like as space expands, there's just more of it. So it seems to be a property of space itself. So as you stretch out the space, there's just more of this thing because it's a property of space.
So it's fighting gravity? So you'd expect if there was only regular matter and dark matter, everything would
Yes. Yes.
jump up. And
Yes.
because it doesn't, we postulate this dark energy to push everything
Yes.
away?
Okay, yes. Good question. So it is fighting gravitational collapse. I would be careful about saying it's fighting gravity just because I just don't want it to mean that it's not explained within like Einstein's theory of general relativity, which is usually how we describe gravity. Because this sort of dark energy can be explained within that theory. I would say that it's fighting gravitational collapse in the sense that you're absolutely right. If we didn't have dark energy, eventually the universe's expansion would slow down and then compactify again. So we would have that big crunch. That said, dark energy cannot fight all gravity. Galaxy clusters will not be ripped apart by dark energy. Galaxy clusters have an immense overdensity of dark matter, a big dark matter cloud that's hugging all of these galaxies, keeping them together. Those will not be ripped apart, but the next galaxy cluster over will be gone. Yeah, at some point, just because of the expansion of the universe and dark energy pushing things apart, at some point, that cluster will be so far away from us and moving away from us so fast that light from it will never reach us again. So it's a very lonely universe if dark energy wins. Yes?
Where do you stand on the concept that maybe it's just our math can't explain the effects of either dark matter or dark energy? Dark energy more important? Or is it some actual unknown?
That our math can't explain it. Like, math bleeds into physics so much that it's difficult to draw a line between the two.
Yeah.
But I mean, if I was a string theorist, you should maybe invite a string theorist. They will tell you a better answer to that question. But they might say that yeah, there are things that we can do with math to explain dark energy. Yeah.
I mean, isn't that where it comes from? The lambda. It's an element in his math that he had to introduce to make other elements work.
Okay. I see where you're going. Not quite. Even if he had not introduced this, we would still find something that behaved exactly like this part of the equation. So we see enough evidence of it that this, I haven't put it up in this equation, but this also exists in that equation. And we would just find that just based on observations. Yeah.
So it's empirically manifested in the math.
Oh yeah, like 50 sigma. Like, yeah. Yeah.
Could dark energy and dark matter just be different phase transitions of each other?
Yes. 100%. There's so many theories we've all been writing down about this stuff. Yes, yes. Phase how do we go over phase transitions?
It's hard.
Yes. Well, we can think about. Sorry.
Aren't you glad you came?
Okay. Actually, Chris might have been a good person for phase transitions. This friend of mine who's visiting, that's my husband, but the other friend of mine who's here is, she's a particle experimentalist, so she like builds things and collides things and then sees what comes out and tries to find new physics. She's very cool. Anyway, so, Chris. Chris, can you explain phase transitions?
Deer in the headlights. No, it's passé.
Okay, we can think about phase transitions more simply, say like water to gas or liquid to solid. That's also a phase transition that happens to be a phase of matter. We describe it in a bunch of different ways. We describe it, say, for example, with pressure and volume, or pressure, volume, and temperature, ideally. We similarly have phase transitions with other species like dark energy and dark matter. Here, a phase transition would be a similar sudden change in its properties. You can have a phase transition in various different ways, depending on how you write down your equations. You can just pick the property that you want the phase transition in, and you can try and write down a theory that suddenly changes that property. Yeah.
You believe that?
Oh, yeah.
What is the typical dark matter distribution within a galaxy cluster? Is it completely surrounding the whole cluster, or is it just sort of around each individual galaxy?
I have a slide for this. It is, let me see, this slide. It's roughly 1 squirrel of dark matter per Earth.
Like galaxies have their own separation, so is it like one galaxy here surrounding dark matter and another galaxy over here? Nothing in between.
No, there's going to be a huge cloud of dark matter. It's going to be a little bit more dense near the galaxies, but not by much. So there's actually a huge cloud of dark matter that's surrounding multiple galaxies. Yeah. Okay. All right. It seems like that's all the questions. Thank you so much.